XRS is primarily a spectrometer, and that is to say it looks at the spectrum of photons that come from a given source. The spectrum will tell you how hot it is, what it's made of, how fast it's moving. So, if you put light through a prism, you get a spectrum of colors. Same thing is true of X-rays. There's higher energy, shorter wavelength, and then there's lower energy, longer wavelength.
How can X-ray spectroscopy help us understand an X-ray source in space? Think about it like this.
So there is a stadium, and people are playing different games in it, and they're using different balls. And the guy or the woman is standing there outside, and then from time to time they get a ball. They look at the ball and they know what game is played. Spectroscopy is this, is the ability of telling what are the different phenomena that occur, say your stadium is like a black hole, or those, near a black hole. And let's say each phenomenon in physics is going to be a different game. And so you want to know what are the games that are played, so you want to get the balls, okay? So let's say you get a football and you say, okay, well, they're playing football. Well, you don't know where they're playing football. So now you need something which is like a good imaging, which is Chandra, for example. Chandra is going to tell you, oh, I know, because if I do an image of the stadium, I know where they're playing football. They're playing football right here in that corner of the stadium.
The X-ray spectrometer is so sensitive that it can detect extremely subtle differences between individual X-ray photons.
If you play football like I do, which is a lot, I'm a pro, I'm a total pro. You can actually play football with ping pong ball if you don't know how to play football, but you also can play football with real football that you have burned so that they have a better, a better grip. This is a trick for pro only. The game is really to have an instrument which is good enough to tell you the difference between the burned football, the non-burned football, and the ping pong ball. Astro-E2 is going to tell you the difference between those three.
Work on Astro-E2 is happening at the NASA Goddard Space Flight Center and in Japan simultaneously. This requires members of each team to travel between Japan and the United States to ensure that hardware and software components are compatible.
One of the things I really like about this project is working with the Japanese. There's some very hard-working people over there, and they're a lot of fun.
These trips also offer the chance to see old friends again. Yet, working with colleagues on the other side of the Earth can be challenging at times, especially when you have two very different cultures working together.
We have completely different cultures, customs, and systems, but we are working for the XRS on board Astro-E2, and we have same goal.
Communication can be slow when dealing with a 13-hour time difference.
We do a lot of emailing. Of course, you can really get sort of one round of email per day because mostly they're asleep over there when you send it, and they answer it during the day and come back the next day.
Then there's the language barrier.
Our counterparts, almost all of them, speak English at some level, and that was really good for us because very few of us speak any Japanese.
When I was in the US, I learned a lot because they all speak English only. They don't speak Japanese, so I had to learn English.
Sampling the cuisine can be fun.
I really like sushi, and there's various other kinds of foods that I like a lot.
What surprised me most is that few Americans eat sweets at the end of lunch or dinner. That's very surprising for me. In Japan, I think sweets are for children or women, not for men.
Here at Goddard, we're building the 5 X-ray telescopes, or XRTs, and we're also building the XRS, which is one of the instruments that looks at the X-rays coming through these telescopes.
That is, the work is simultaneous, but it's not linked together by schedule. You just all have to be at the spacecraft at the same time.
Most assembly and testing of the XRS instrument is done here in the Cryogenic Integration Facility, or CRIF for short.
At the very heart of the XRS instrument is the microcalorimeter array. This is a very small detector, but it has unique and powerful capabilities. The final steps of its assembly are done in this laboratory right here. So let's go and see what all the fuss is about. This is the XRS microcalorimeter array. Essentially, it's an array of very tiny thermometers designed to measure the temperature increase that occurs when an individual X-ray photon is absorbed.
To detect the minuscule amount of heat given off by a single X-ray, engineers must employ cryogenics, the science of the super cold.
Now, in order to make a good spectrometer, the detector needs to be very cold.
An ordinary object doesn't change much when an X-ray hits it. So making it cold helps in 2 ways. One, it means that the temperature change is a larger fraction of the temperature it's sitting at. And 2, the heat capacity of almost everything goes down very rapidly as you get close to absolute zero. So a little bit of energy causes the temperature to rise a lot. So we have to keep it very, very cold.
We have to operate this detector at 60 millidegrees above absolute zero. So that's what the rest of the XRS instrument does, is it makes this really tiny detector cold.
When you're trying to keep something that cold, you usually have to have a multi-stage system, and we do that as well. There's an outer layer of solid neon. That's 17 Kelvin. That's pretty cold for you and me, but it's still blazingly hot for our detectors. So inside that, there's a layer of liquid helium. And that's helium like in your helium balloons, and that's at about 1.3 Kelvin. And then inside that, there's what we call an adiabatic demagnetization refrigerator, which uses magnetic spins inside actual atoms and aligns them and de-aligns them in such a way to get us down to 60 millikelvin. The XRS detectors are placed inside a dewar. A dewar is like a thermos bottle. If you have a real glass thermos bottle to keep your coffee in, that's a dewar. And it's 2 walls, and in between the walls is vacuum. So the